Okay, I agree that this is a poorly worded problem because there's no real definition of what we mean by next to each other and what dimensions of what minimize the amount. But let's make some assumptions here that the pens look like this. They're in a rectangle with these shared walls between compartments. The drawing is not accurate because I didn't make them all look identical. But if we label each of these vertical walls X and each of these horizontal walls dividing the uh, length of the rectangle in 5 instances of Y, we know that the area of each pen is 375 square feet squared. So this relationship holds. And that allows us to give uh, y in terms of x. Y equals 375 divided by x, or 375x to the minus 1. So the total amount of fencing is 1, 2, 3, 4, 5, 6 x's plus 10 y's. But we know that y is 375x to the minus 1, which I could write as 3,750. If I find the derivative of that function, I get 6 minus 3,750x to the minus 2, or over x squared. Setting the first derivative equal to 0 right here. To find critical numbers, that is concluded over here. 6x squared equals 3,750. Divide by 6. Take the square root of both sides. X is 25. And if xy equals 375, y equals 15. Now over here, I took the second derivative of p with respect to x. Applying the second derivative test, I plug this critical number into the second derivative. It's easy to see that this will be a positive number, which implies that the curve at the point where x is 25 is concave upward, positive smile, smiley face. So 25 is generating a minimum at that point. And if I share my screen and go to Desmos, here's a picture of that function with some value substituted. It looks like when x is 25, we do have a minimum amount of fencing, 300. Okay, there you go. Hope that helped. If you have any questions, post a comment.